All right, so this is the last lab of the term, so you guys should be happy about that. Now this lab, you know, it seems like the oscillations and the waves seem to have a lot in common. Now they have a lot of common nomenclature. You might wonder, do they have any kind of a intimate relationship, if you will? You know, and the idea is, well, typically when you do a physical lab, like we were to actually meet face to face and do a lab, you would typically will create waves by essentially having an oscillator. So I drew a little picture here on the board. I think you see it. You have an oscillator here that's going to be essentially a device. Well, this is a wave on a string. You know, one of the things we're going to do tonight. So this is so you have a string that, you know, if it wasn't for this thing oscillating, it would just be a string that's, you know, essentially flat and across. But then you have this oscillator. It's going to go back and forth at some sort of a frequency. Now that oscillator is going to give you the disturbance that's needed to create the wave. Remember, the wave is a disturbance that propagates. So the disturbance in the string, there'll be a vertical disturbance that'll cause it'll be a disturbance in the y direction. It'll cause a wave to propagate in the x direction. This is an example. The wave in a string is an example of a transverse wave because the disturbance is in the y direction and the propagation direction is in the x direction, where the x-axis is perpendicular to the y-axis. All right, and so you notice here that I have an oscillator that goes to some sort of a frequency, and what you see is, you know, a wave like we talked about last time, nomenclature from last time. I'm not really going to talk about. I'm just going to redraw the picture briefly, but you know, we already discussed this in the previous lab session, and I've discussed this in the videos. Lambda is the wavelength. Again, the wave repeats itself. It's periodic, and so the wavelength is essentially the distance between, you know, this wave is traveling in the x direction. So if I were to imagine myself, you know, standing at some location, and at this point, let's say at this point here, I'm going to notice a crest going by, and the wavelength is the distance the wave travels until the next crest goes by. Or I could look at from trough to trough, or however I want, as long as it's some sort of a distinct part of the wave, and I wait for that same distinct part of the wave to come by again and repeat itself. That's the wavelength. How many waves pass by, you know, as I'm viewing them, how many waves pass by per unit time? That is the frequency. That would be in hertz. And 1 divided by the frequency is the period, and that would be in seconds. How long does it take for an entire cycle to pass by? That would be what's called the period. So again, there is an intimate relationship between the two. It's no accident that the oscillator terminology, I mean, I didn't want to talk too much about it as we were learning it, because I think it'd be more confusing. And now I think that we kind of have nailed down oscillators and we've nailed down waves. Now we're advanced enough to discuss the relationship between the two. All right. And so you would invoke that relationship in the lab. And so, and in fact, if we were meeting face to face, you would do a lab, you would do a sound lab, and you would do a wave on a string. You would pretty much do exactly as we're doing tonight in the simulation. You would set that up in the lab. So really, tonight's simulation is very similar to one of the labs that we actually would do face to face. All right, and so there's a lab where it's a little eerie after a while, because you walk by the room and all you hear is you hear these loud sounds everywhere, you know, and they hear, you know, and another person's got a real high pitched sound going up and down, and so as people walk by, they hear all these sounds going off in the lab, right? So it's one of those labs. It's a very noisy lab, and so essentially, you know, and then you'd have a wave in a string. You have an oscillator going back and forth, and you'd be creating waves in the string. In fact, you'd be creating what we call standing waves. Now in tonight's lab, we're gonna allow for there to be a free end. You know, so we're gonna allow the wave to go on forever. A standing wave means you're crimping it on the end, and you're actually creating waves that really are oscillating in place. And we'll briefly talk about other kinds of waves, but for the most part, in the actual wave on a string lab, we're just going to be talking about standing waves. And that's really all I'm going to talk about in theory. All right. Now, I want to remind you guys of something as well. So this class was very lab heavy in the beginning. Toward the end of this class is going to be very exam heavy. All right. And so, yes, you have an exam this coming Thursday, but you also have an exam next Thursday. All right. And so if you've been looking that far ahead, just kind of give you a little, I'll send an email out for, I mean, there's about 10 of you here. For the other 10 of you who aren't showing up, I'll try to send an email to capture that. But, you know, so on July the, hey, really running out of me. There we go. On July the 16th, which is this coming Thursday, you know, again, we have exam 2, as you all know about. And that exam is over chapters 5, 6, 7, 8, 9, right? Now, exam at 7, exam July 23rd, we have exam 3. Now, what I'll do is toward the end of this week, toward the end of this week, I'll send out a review for that. So toward the end of this week, I will send out a review for exam 3. It'll be kind of like what problems you want to look at. Now, I guess this is up to you. For the 10 of you who are here, you know, you guys have shown up to vote essentially. Would you want? I mean, I can do a review, but maybe move it up instead of having, let's say, I mean, again, we're crunching at the very end, right? But I would say maybe Monday. This coming Monday instead of Tuesday, had the review. That sound better? Because you're having the exam on Thursday, and so I'm assuming most of you guys have something going on Friday. But I would say the next time we would meet would be Tuesday, and we could just meet to do the review. We don't have any more labs after tonight. Or would you guys prefer instead of meeting Tuesday, we meet Monday? Give me an extra day to study. Would you want to do the review on Monday? So Monday would be what? It would be the I guess the 22nd. No, not the 22nd. What am I talking about? The 20th. Is that something that'd be better for you or no? Or would you rather?
For me, it is.
Yeah. Is there anybody that cannot do Monday night? Who's in this room? I mean, the other 10 didn't show up to vote, so. Out of the 10 of you guys who are here, is there anybody that cannot do a review on next Monday? I'll send an email out to review, so we'll do that. So that would be so Monday. So let me so again send a review. So Monday, I can do the math right. That'd be the 20th. Yeah. So Monday. I normally get more days, but we're just rapidly running out of days, right? So Monday, July 20th, we'd have we just meet to do any kind of an exam 3 review. So exam 3, I usually have it being 10, 11. I usually do 11 through 10 through 13. You know, usually in exam 3. So so we will do. I'm going to save the waves till last. We already done the waves, but I moved them up for the specific purpose of having to be able to do these labs. But so essentially, you have chapters 11 and 12 videos from last weekend. I will do the videos for well, let's see, how will we do that? Maybe I should move the waves up. Let me think about that. Yeah, it's probably 10, 11, 16, 17. That's probably what we know to do for that. So yeah, we'll do that. So exam 3. We'll most likely, most intelligently would be, I guess, chapters 10, 11, and then you've done 16 and 17. So while it's fresh in your head, you might as well do that. And then exam 4, and I'll figure out when to do the review for that, but the exam 4 looks to be on August 3rd. And that would cover what we haven't tested on. So that'll be 12, 13, 14, 15. That would be, yeah, that would actually make a lot more sense. That would be entirely thermal physics. So here we'd have the remaining parts of mechanics and then waves, and then the last exam we would just do thermal. All right, and so let's do that. So, all right, so anyway, that's a peek into the future. So look for some review problems toward the end of the week for me. Okay, all right, so that's all I want to write in the whiteboard. Unless you have any questions before we go into the lab. I don't see tonight's session being very long, certainly not as long as the last one. Last one we did a combo lab and review. In the future, this is the last lab, so in the future, any kind of time we get together will be more or less just to, there's very few days left in the term, so most likely we're either gonna meet to do a review or meet to do an exam. So that's pretty much all that's left, right? So, all right, so let's, let me fire up the first lab. So I have no questions at this point. Alrighty, let's bring the lab up. Yeah, we shouldn't be here. Should still be daylight, I think, when we're done. All right, so do the sound lab. That's the first. Come on. What in the world am I doing? Here. My computer's acting weird now. All right, here we go. All right, bringing up the sound lab. Now, you fire up this lab, you're going to want to have your sound card, any kind of sound settings on your computer turned on. I guess for right now, I would say if you're going to play the sound, I would say probably turn off your microphone so not everybody else hears it. I'll just play my sound. Everybody can hear that. That's probably sound labs. You start hearing other people's sounds too. All right, so I'm firing up the lab right now, so you're not seeing anything quite yet. Okay, I had no problems bringing this lab up, so I don't think you guys will either. All right. It's almost there. It's scanning scanning for viruses right now. Okay. Oops. Here we go. Open file. All right. So McAfee needs to try to protect me. All right. So I'm bringing up the file. Sorry, it's this deliberate. There we go. Oh, my goodness. It takes a month of Sundays to come out. Okay, here we go. So let me share my my view. All right, so what you should see is a picture of a guy with a speaker next to him. Now, what we see here is, as I've been talking about, an oscillator creating disturbances. Well, a sound wave is a longitudinal wave, and so what inside of the speaker is a cone that oscillates. So the cone is creating a pressure disturbance in the air, and that's exhibiting itself as a sound. So it's creating sound waves, or basically pressure waves. And so that's what your ear hears. The sound waves will actually vibrate the eardrum and create, and you perceive that as sound, and that goes to your brain's information. All right, and so you notice that there's a little pulsation right before the bell of the speaker, the little bell shape of the speaker. So that's your cone that oscillates back and forth, that creates the disturbances. So again, that's your oscillator this time. What I drew was an oscillator that essentially caused a transverse disturbance in the string. Here is and again, a wave in a string is a transverse wave. The sound wave is a longitudinal wave. All right, but it's the same principle. You have an oscillator that is causing a disturbance. All right, so that's what you're seeing here. Now, what we're going to do is this is going to be kind of a little bit of a noisy kind of lab. It's going to have sounds in it. Probably it might be a little bit unpleasant. But as you look through here, say, okay, well, we're going to listen to a single sound. So we're going to go to the single sound tab. That's already selected, the single sound. And in the sound waves lab, and we're going to turn on the audio enabled. All right, so audio enabled is a check box that's off to the right. You click that, and then when you change, and then so you can hear the sound. So you should, okay. So now you start hearing the sounds. Okay, so it's kind of, not very pleasant. So whoops. Yeah, I hit the wrong thing. Now, what you can do is you can move the couple different slider bars. The top slider bar is the frequency slider bar, and the lower bar is the amplitude slider bar. So the frequency is going to create the pitch. So if I move the frequency slider bar to the right, it increases the pitch. Right? So I went to 500 to 687 to 800, and I'll go back down to around 500. Back down to 500 hertz. And if I go to a lower frequency, it lowers the pitch, 384. And so what that's causing is if we kind of notice, the oscillator is moving a little bit more slowly, more slowly in the case of the lower pitch sound. And you see the wavelengths not being as rapid in time as when I do the higher pitch. You'll start seeing the oscillator going faster, a more vigorous pulsation, and you'll see the waves. You'll see more waves per unit time. So kind of keep your eye on the waves as they appear right now. And as I move the slider bar to the right, you'll see the waves becoming more. The pulsation is a lot faster, and the waves are coming at a much greater rate. All right, so that's the pitch, that's the frequency. So the frequency can be directly perceived by us. We cannot perceive wavelength, but we can perceive frequency. So let me kind of take it back to 500 again. All right, and now the amplitude, on your hand, the amplitude is going to be how large the oscillations are going to be, not how many of them are unit time, but how big the actual how much the oscillator goes. What is its amplitude? How much and why, or how much in the direction of oscillation does it actually go? So you'll notice that if I take the amplitude to be smaller, it'll become quieter. So it becomes quieter when it becomes smaller, and you notice that the waves become more faint. You don't see them quite as easily, and really the cone is vibrating just as fast. It continues to vibrate. I have it at 495 hertz. It vibrates just as much. It's just it doesn't the the amplitude of the vibration is not as much. Now, if I take the amplitude to slide it to the right, it'll become louder. So it becomes a larger amplitude. And so essentially, I have not changed. If you notice, the faint waves versus the more easy to see waves, they have stayed the same frequency. They've just become, and the pulsation becomes larger. All right, so that's the whole concept of the amplitude versus frequency. So for number one on page on the first page, the front page, you want to describe what you just saw. Number one, so it says when you change the frequency, how does the sound change? How does the visual model change? I mean, I talked about that. Change the frequency, the sound, the pitch increases when you increase the frequency. The pitch reduces when you decrease the frequency. And you'll notice that that essentially the pulsations become more rapid. The oscillations are causing the disturbance that becomes sound waves. And let's change the amplitude due to the sound. Well, the amplitude makes essentially the pulsations become larger each time. And when you increase the amplitude, and you effectively increase the loudness. And if you reduce the amplitude, the pulsations become have a smaller maximum. About the center point. However, and the sound becomes more faint. All right. So it says sound is produced. So I'm going to put this on pause for a moment because it is a little bit annoying. Sound is produced when something vibrates. So this is number two. The movement causes disturbances in the surrounding air pressure. Investigate how a speaker cone moves to produce different sounds. Then explain the relationship between the movement of the speaker cone and the sound that is made. You include drawings. Well, effectively, the cone that you see pulsating is an oscillator. And as it moves, the more rapidly it moves, you're creating more waves, creating a time, hence you're creating a higher pitch. The greater the distance for each oscillation, that's the amplitude. So again, that is the relationship between the sound wave and the oscillator. Okay, the oscillator creates a sound wave, right? So again, kind of say some words about that. That's the bottom of page one. Okay, I'm on page two, top of page two, number three. Use the tools on the measure tab to find the speed of sound in air. Make a data table that demonstrates you have a good experiment and show sample calculations. So I'll do one calculation for you. If you want to do a couple calculations, kind of check yourself, maybe take an average. And then how do your results compare with what's published? So typically, if you looked at my chapter 17 video, the speed of sound at 0 degrees Celsius is about 331 meters per second. The speed of sound at 20 degrees Celsius, and there's a square root formula that I give you in the video to help you calculate the speed of sound. But essentially, the speed of sound at 20 degrees Celsius is about 343 meters per second in air. Okay, we're assuming air here. Okay, so again, look at my chapter 16, 17 video. I explain all of this. I explain, how the speed of sound the speed of sound in air depends on temperature. Okay, I gave you the formula there. Okay, so I guess let me just kind of put it up to remind you. If you haven't seen the video, hopefully you've all seen the video by now. But speed of sound in air, there's a nice ready formula. I brought this down. So remember, speed of sound in air given as B equals 331 meters per second times the square root of T over 273. All right, T is the temperature in kelvins, must be in kelvins. So I talked about the Kelvin temperature scale in the chapter 12 video. Essentially, the whole world, except for us, works in the Celsius scale, and we work in this Fahrenheit scale. Celsius is nice because it's a nice power of 10 scale, the 0 to 100 scale, and it's based upon one of the most important substances to humankind, water. And so what's more important to humans than water? Very few things are more important than water to us. So we set 0 as the freezing point of water, and we set 100 as the boiling point of water. Very convenient. Celsius has weird numbers like 32 for freezing and 212 for boiling, right? Don't ask me why. But when we get smarter, we understand that there's actually atoms, and that the temperature is actually a measure of the average kinetic energy of the constituents of a substance, i.e. the atoms and molecules, their average kinetic energy. We call that the thermal energy. The greater the temperature, the greater this thermal energy. The lower the temperature, the lower the thermal energy. So if you keep lowering the temperature and lowering the temperature, you're lowering the thermal energy more and more. Might there be a situation where you find a temperature that is so low that things just stop moving? And that temperature would be what we call absolute zero. Now, the third law of thermodynamics states that you can never achieve absolute zero. Again, I state this in the lectures, but that's, we have 4 laws of thermodynamics. The third law basically says that you can only asymptotically approach absolute zero. You will never get there, right? No one ever has. So now, do things actually stop moving? Well, the answer is they do not, actually, if you consider quantum mechanics. In quantum mechanics, even in empty space, you have what's called a vacuum energy fluctuation. You have vacuum energy fluctuations that are random fluctuations of energy. And you'll never have zero energy. You'll always have these fluctuations. And some fluctuations are bigger than others. Most of them are about the same size. These are also called quantum fluctuations. And as theoretical physics states in the standard model of theoretical physics, our universe began due to a very unusually large vacuum fluctuation that would happen 30.7 billion years ago, called the Big Bang. And so vacuum fluctuations are important. In fact, we're here because of a very unusually large vacuum fluctuation. And so essentially things really never do stop. They're always in motion. But in the classical mind, for the person who lived before 1900, absolute zero is where things stop moving. So we can take a temperature scale and based on absolute zero, where 0 Kelvin is this special temperature called absolute zero. And you add, so you want to get Celsius, basically you would do what? The Kelvin temperature would be the Celsius temperature minus 273. All right. And so you'd say, okay, well, 0 degrees. I'm sorry, that's backwards. So it'd be plus 273 Kelvin. So you want to say 0 degrees. So basically, what is 0 Kelvin is the same as negative 273 degrees Celsius. Freezing point of water is 0 Celsius. That's the same as 273 Kelvin. The boiling point of water is 100 degrees Celsius. That's the same as 373 Kelvin. All right, and so it's a nice, easy formula to get there. And I gave you in the video, I gave you the formula to get from Fahrenheit to Celsius. I mean, you guys have probably certainly have seen this before you came to this class. But anyway, you have to use Kelvin temperature here, all right? And so we should be seeing a value around 340-ish, 330-ish, whatever we do this right. I mean, honestly, this is so rough. You're lucky to be even 320 would be probably a fine number. So anyway, let's go back to the lab and see how we go about doing this. All right, so what I'm going to do is I'm going to get an estimation, and so I'm going to essentially get out a, hang on one second. I'm going to go to the measure tab. So it tells you on top of number 3, we're to listen to a single source tab. Well, you click the measure tab, and the measure tab actually, that guide goes away. What you now have is a ruler that pops out. So what I'll just do is I'll just kind of try to put my ruler right around where I expect to start taking a measurement. So I'll just line up 0 right around the lip of this speaker. Do the best I can. It's gonna be a rough measurement. That's the best I can do. And then I have this simulation. And all I do is I'm going to kind of do a similar thing. I have to kind of time it. And so I'm going to hit pause for the moment, and I'm going to reset things. And I want to actually then, so I have it at 0. I'm going to hit start so that when I select start, or when I select the play button, the timer will automatically go. So I already hit start, but you don't see anything happening yet because I haven't hit the play button. So I have the ruler lined up, and now what I'm going to do is I'm going to try to watch a part of the wave, and right now I have this, looks like a formation of a little white semicircle that's going to start expanding out. Looks like a crest, the very front of a crest. I want to watch that crest and basically try to hit the stop button right around the time when that crest reaches, say, around 5 meters. I mean, it's going to be rough, and again, I'm not known for my coordination, but you kind of watch, see that crest that you see right at the speaker. I'm going to hit the play button. I'm going to try to hit the stop, but I'm going to try to hit stop right around the time that crest gets around 5 meters, if I can. So I'm going to try to follow it, and I'm going to try to time how long that takes. So I'm going to try to time how long, basically how long it takes for this wave, this particular wave to go 5 meters. So see how good of a job I can do. All right. And actually, you know what? I already screwed up. Hang on. Stop it. Reset. I looked away. All right. Let me try this again. It's gonna be rough, but okay. So I'm in this little black area here. All right. So I'm gonna try to watch it. I didn't quite do a very good job. Let me try this again. Sorry. Reset. All right, I'm gonna try this little right at the end of this white circle. I'm gonna take, there's a little end of a white circle right at the edge of the speaker. I'm gonna try to see if I can stop it right when it hits the 5 meter mark, or the 5. Yeah. All right, here we go. All right, that's about as good as I can do. Oh, I didn't time it. All right. All right, sorry. All right, that's probably about as good as I can do. So 0.0161 is roughly what I got there. So if I write down, so I got T equals 0.0161. So let me go back to my whiteboard. And all I did is I just followed some part of a wave in this very, very rough experiment, figured out how long, I timed it to be, how long did that take? I think you do a better job of me by doing this experiment yourself, but how can I find the speed of sound in this very crude experiment? Well, I measured that it took 0.0161 seconds. So the wavefront that I watched traveled, we'll say D equals 5.0 meters roughly. There's a lot, you can see there's a lot of error to this experiment. And about T equals 0.0161 seconds, right? And so what's the calculation for the speed of sound? Very complicated. It is V equals D over T. And so it'll be 5.0 meters divided by 0.0161 seconds. And let's see what I get when I do that calculation. 5 divided by 0.161. Oh, that's not right. 0.161. 5 divided by 0.0161. I mean, not terrible. 300 and I say about 311 meters per second. It's a little bit low. All right, and so, I mean, again, it's a computer simulation, but you know, I'm in the ballpark. I would hope to be right around 330. I get about 311. And again, there's sources of error, would be my measuring error. I'm not known for my hand-eye coordination, things like that, right? So, but anyway, you know, it's in the ballpark, and so that's roughly what you want to do in that experiment. Is you kind of just want to, you know, kind of set up your timer just right and follow a part of a wave and see where it crosses, you know, 5 meters roughly. And that's all that is. So again, nothing. You're trying to do a crude measurement of the speed of sound. Okay. It's basically how long, you know, you have this disturbance, how that disturbance goes 5 meters and at what time, and that distance over time is the speed of sound. All right, so let me go back to sharing. So that's all that's to that lab. This is a very crude measurement of the speed of sound. Any questions about that? So next, number 4, so on page 2, how could you find a wavelength of a sound? Test your idea with several different sounds and check to see if the results for the wavelength make sense. Well, what I essentially said as well, I can find a wavelength by essentially figuring out, well, a couple of different things. I can take a look at the 5 meters that I'm seeing here, and I can kind of check things a couple different ways. In a very crude way, I can see, okay, well, in 5 meters, how many crests do I see? Well, I can kind of see how many white crests do I see. 1, 2, 3, 4, 5, 6, about 7, maybe 8. And so I'm talking about 5, you know, so I'm just going to do a quick little calculation here, show my board again. So and also let's note that the frequency here is 500 hertz. That's what it reads on the side. So let's kind of check it both ways. So we're kind of seeing that you see about, again, this is very rough, simple experiment. And you're seeing, well, I can kind of check it a couple different ways. This is the speed of sound that I'm calculating, about 311. So I'll kind of put it in the parking lot. All right. And let's kind of, for this very crude experiment, let's kind of see if we can get a couple of different estimations for the wavelength. Well, essentially I have 5 meters is good for about 7, maybe 7.5 cycles. Well, we'll say 7.5 roughly. I mean, because I saw part of a, we'll say 7. I mean, so lambda would be what? It would be the total distance that the wave traveled, about 5 meters, but that's equivalent to, looks like 7 full cycles. I mean, I counted about, again, this is very, very, very crude math. I counted about 7 full cycles, and 7 full cycles took about 5 meters. So one way of looking at this would be, okay, 5 meters divided by 7 cycles. I'm looking at a wavelength about 0.71 meters, roughly. I can also look at it this way: V equals lambda F. I just got done computing a speed of sound, and I know the universal weight formula for waves, and I know I can read on the display that the frequency that is set is 500 hertz. I can see that in the display, so I should be able to get a number that more or less agrees with my crude estimation of the wavelength by using this formula. So I can say, okay, well, wavelength is that speed of sound I just got done computing divided by the frequency. So I had 311 meters per second divided by 500 hertz. What's that give me? I mean, again, it's going to be rough. 311 divided by 500. About 0.62. So maybe I should have used 7.5 here instead. What if I did 5 divided by 7.5? 0.66, 0.67, right? I mean, again, it's rough. So maybe I saw part of the crest. I saw part of that crest, you know, before I did it. I mean, it wasn't, you know, some of the wave had already traveled. Let's just say, call it 7.5 waves. I mean, again, rough back of the envelope calculation. Maybe instead this might be 0.67. But you can kind of see for how crude this experiment is. That we're getting wavelengths that if you were to ask what the wavelength was, I'd say, it's somewhere between 0.6 meters and 0.7 meters. I don't know it any better than that. This is a very crude experiment, but I mean, it's about 0.6 to around 0.7 meters. That would be what I would say from this experiment that my wavelength would be somewhere in that neighborhood. My experiment's no more precise than this. It's not a very precise experiment. It's very crude. So I mean, I'm not. But anyway, that's, you know, it's the nature of this lab is that, you know, this is not a precise lab. If we wanted a precise lab, we'd meet face to face, right? So you're really measuring how well some programmer wrote software, right? So, all right. So I'm on page number 2 still. Number 5 says describe how you might use the simulation tools to find the period of the wave without the frequency information. Well, I could do this. You want to find the period? Well, I could do it roughly the same thing. So I saw that there are about, say, 7.5 waves, right? And how long did this all take? So I'm going to erase this. How long did it take for 7.5 waves to pass by? Well, we read it was what, 0.0161 seconds. So the period, the total time was about 0.0161 seconds for this whole wavefront, you know, to actually pass by. But during that amount of time, I saw roughly about 7.5 wavefronts or 7.5 waves. So the real period, you know, that's the time it took for about 7.5 cycles to travel. Well, how much time would it take for one cycle? Well, I divide by the 7.5 that I saw, and I get a period. Again, you know, for all the advanced math we've been doing in this class, this is the Mickey Mouse math. So 0.0161 divided by 7.5. So I'd say the period's 2.15 10 to the negative 3. Well, and again, I'm supposed to do this without using the frequency. Well, let's check it versus the frequency now. We saw in the display the frequency is about 500 hertz, right? So I can check by saying, well, I should see a number that agrees with some semblance of sanity. So I can read on the display 1/500 hertz. Well, that should be about 1/500. And 2 times 10 to the negative 3. Yeah, pretty good. So again, from the experiment, I can get some decent idea about what the period is, and I can check that by a more formal calculation because presumably the software must know the frequency fairly well, and so period is one of our frequencies. So I should see a period that, and this is not too bad of agreement. 2 times 10 to the negative 3 seconds compared to 2.15 times 10 to the negative 3 seconds. That's not bad. I mean, that's quite good for how crude this experiment is. Okay. Any questions? I mean, I'm on the bottom of page 2 now. And the bottom of page 2 is very similar. Describe how you would find the frequency of a wave if the frequency slider did not have the number displayed. Well, real simple. If I didn't know that frequency, let's say, for instance, I didn't see that frequency value on the slider. I had no idea. All I knew, but I did know this much. I mean, I didn't have any idea, but I did know this. This is the calculation that I got from just saying, well, this is how long it took, my stopwatch, divided by 7.5 waves. I have a period of 2.15 descending at 3 seconds. Well, if I don't know, if I can't read this frequency on the slider bar, if it's not displayed, I can get to it. I can get some estimation of the frequency by just taking the period that I measured and just saying, oh, how about the frequency is 1 over the period? So what would that be? Be about 1 over 2.15, pure measurement right here. Just me, my stopwatch, and counting waves, right? 2.15 times 10 to the negative 3 seconds, and I'd find out that my frequency, that my estimation would be, if I knew nothing else, 1 divided by 2.15, 10 to the negative 3, about 465 hertz. That's what I'd get. I mean, that's not bad. But that would be my estimation of frequency if all I knew was this. I'd say, okay, well, I have an estimation of the period. 1 divided by the period's frequency. Again, that's as good as I can do if I don't know anything else, and the crudeness of this experiment. Okay, so I'm done with page 2. Any questions of this? That's the sound waves lab. Okay, now we're going to go into wave and the strings. Before I leave the sound waves lab, does anybody have any questions at all? All right, take that as a no. All right, so let me fire up the second of the 2 labs. That would be the waves on a string. All right. So let me bring this guy down. All right, back to the Word document. Okay, second link. Uh-oh, did I do this right? Word is not responding. That's not good. Hang on, we got to get Word to respond. All right, here we go. Word came back from vacation. Here we go. No, still not responding. All right. Hey guys, I'm fighting the software. Here we go. I think something's happening. I don't know if you how much experience you guys have with the software, but there seems to be about a half a minute where you have no indication that anything's happening at all, and all of a sudden you start seeing something appear. So, before that, you don't really have any idea if anything's actually any software. Oh, here we go. Yeah, it actually is coming up. So I was about to give up. All right, wave on a string. I'll select the play button, and then I'll share. Still loading. It's coming. Okay, let me move my window a little bit and I'll share. Why is that still up? I have a sound still up someplace. All right. Anyway, let's just continue. So what you should see is what looks like a set of red and green beads, and it looks like a vice grip on the right side and some sort of mechanical device on the left. What we're gonna do you guys all see that?
Yes.
Okay. So what we're going to do is follow his instructions. And he wants to select oscillate. So you have manual, oscillate, and pulse. We'll select oscillate. Somebody knocking on the door, but oh well. All right, so oscillate, I'll select that. And you start seeing the wave oscillating. It's going to be no end. So on the right hand side, you either have a fixed end, a loose end, or no end. And all kinds of things going on, right? No end. All right, and then you'll have want to select slow motion to kind of slow everything down, so we can actually kind of calculate things. So I'm selecting slow motion, slow down the motion. All right, so you'll see it's a wave. So you'll see kind of like what I drew. And again, you know, the display doesn't appear very well over the zoom. But what you see is an oscillator going back and forth, and it's causing a disturbance in the wave. Now, I was a little bit confused about one part of the lab, so I'm going to do a part that my interpretation on, you know, you'll see this on page 5. There's a table on page 5. I had an interpretation. I wasn't quite sure, didn't really understand what he was talking about to some extent. I'll explain it to you when the time comes. But you essentially you're seeing a wave being driven by this oscillator, just like I wrote on the whiteboard. If the oscillator going back and forth at a certain frequency, that frequency is driving this wave. So the disturbance is in the y direction, if I were to consider the vertical y, and then the horizontal is where the propagation of the wave occurs. And there's no fixed, there's no end. Essentially means that this wave will go on forever. There's nothing that's going to cause it to stop. If I were to actually cause a fixed end, that would create a standing wave, and the loose end would have a different effect. There'd be a different boundary condition on the end, the loose end. We'll look into that in a moment. All right, so number 1 says use the amplitude slider. Okay, there's an amplitude slider. So on the bottom, we have an amplitude slider and a frequency slider. We have another slider that's called damping, another one called tension. Again, I'm hoping that you have watched my my videos, and I talk about all this in the context of oscillations and waves, right? But I'll say a little bit more about it. But so the amplitude, again, is going to control. So really, it's going to control how far up and how and down the oscillator goes, and then that will control, you know, the height above the horizontal dash line, which we call the axis, the wave axis, and below the horizontal dash line. So the greater the amplitude, the greater that height. And so if I look at I'm on number 1, I need to take a look at what happens to the amplitude. So if I increase the amplitude, I'm at 0.75 centimeters. If I move it, let's say to the right, I increase it to, let's say, 1.05. You'll notice that the oscillator is going to have larger displacements, and that's going to cause the wave to have a higher maximum and a lower minimum, right? And if I reduce the amplitude, I see the oscillation is not going to go as far. So I'm going to take it down to about, let's say, take it down to about 0.3. Now the oscillation is not going to have as great a displacement, and so the wave will not be as high. So that's what the amplitude does. The amplitude essentially gives you the height of the wave. Now, the amplitude squared is the actual energy in the wave. So waves with larger amplitude have more energy. So you notice that, you know, in the case of sound waves are louder. You take the squared amplitude, that's the energy. You have a louder wave. You know, when you say, you know, people can shatter glass with their voice, you know, well, that's being done by really an amplitude more than, say, a frequency. But anyway, so because the energy of the wave is due to the amplitude. So let's get the amplitude back to normal. So again, what are you going to say? Well, you want to say define amplitude in everyday language. Well, I say the amplitude is the maximum height of the wave above or below the horizontal axis. In everyday language, that's what it is. It's the maximum height of the wave above or below the horizontal axis. And then B, explain how the wave behaves as the amplitude changes using the characteristics you described? Well, the wave height, I mean, if the amplitude is larger, the wave height increases. Or if I select the lower amplitude on the slider bar, the wave height decreases, as you just saw. Explain what you just saw, essentially. Number 2, page 3, use a frequency slider. Answer the questions. All right, so let me get the amplitude back to what it was. I think it was 0.75. Let me put it back to where it was. All right, so that's roughly where. Let's kind of let it settle for a moment. Now the frequency says the answer to questions including images. So again, if you don't want to include images, that's fine. I think if you just, maybe that's maybe more for the advanced class. But for me, if you just kind of explain in words what you see, that's perfectly fine with me. I mean, there's enough. You have enough going on right now without having to deal with images. Use the frequency slider. Okay, define frequency in everyday language. Well, frequency is a number of waves that pass a point per unit time, just like I said earlier. If you were to watch waves and you would just count how many waves, let's say I'm going to watch crests, 1, 2, 3, so on and so forth. How many waves per unit time? That's the frequency. Okay, how many cycles went by per unit time? And then part B, 2B, explain how the wave behaves as the frequency changes using the characteristics you described. So well, we haven't looked at that yet. So we kind of imagine for a moment, we have our experience with sound waves. If I slide the frequency slider to the right, I'm going to increase the frequency. What I'm going to do, if the frequency truly is the number of waves per unit time, I should see more waves per time. So if I increase it, so let's see what happens. So I'm going to slide it's 1.5 hertz. I'm going to slide it over, let's say to, I don't know, 2.74 hertz. And notice that now I have more waves per unit time. I've increased the number of waves that'll pass by per unit time. So pass by some sort of a point. And let me take the damping down to 0, by the way. I'll explain that. I'm going to take the damping down. So damping, when I had damping, the amplitude was gradually getting smaller and smaller. So let's just, one of the things I should have done in the past was take the damping down to 0. So I apologize for that. Anyway, there you are. More frequency per unit time. If I were to get it back, if I were to reduce it instead of 2.73, let's say let's get it down. I originally had about 1.5. Let's get it down to, let's say 0.75. Well, now I have fewer waves per unit time. So when we saw the 1.5, I'd have 1.5 waves per second. Well, now I'm having half of that, 0.75. All right, I guess it's 0.72 now. Anyway, you'll see that the number of waves per unit time, it has reduced. All right, so again, higher frequency, essentially you see more waves per unit time passing by. Lower frequency, fewer waves per unit time passing by. And we're kind of seeing. So let me set it back to where it was before, around 1.5. Yeah, I'll never quite get it there. Here we go. Use the arrows now. So I'm setting it back to what it was before, 1.5. All right. So then so kind of explain what you just saw. Now use the tension slider. Answer to questions including images. All right. So hopefully again you've watched my videos. Let me stop sharing for a moment. Now, if you watched my video on waves, I explained how you get the speed of propagation in a wave, how it relates to the tension. All right, so going back to my whiteboard. In a wave on a string, we can figure out the speed of propagation. And so the speed of propagation of a wave on a string and this is in my video. V is the square root of tau divided by mu. Tau over mu. Tau is the tension in the string. Again, that's the tension. We talked about that in our chapter 4 studies, or studies of forces. That's how tight, the string is pulled, how taut it is. That's the tension. The mu is the linear mass density. That's essentially the density per unit meter, so or kilograms per meter. So if I was doing this lab, I would take a string. So I'd be looking at waves in a string in the lab. If we were to meet face to face, I would take some fishing line, which is what we usually use in the lab. So so a student would take a piece of fishing line, cut it, and then they would take that fishing line. That fishing line was going to be used to do the wave in the string. What the student would do is the student would take this fishing line, put it on a mass meter, so some sort of a scale, put the fishing line on the scale, and figure out what the mass is. Then a student would, once the student knew what the mass was, so now we have the mass. Now the student's going to take a look at the length. All right, so the length, we take a look at the length, and the student would literally calculate mu. Mu is that mass that was read divided by how long the string was. And you want to figure out the tension. What would the student normally do? Well, you would have some sort of a string attached to, you'd attach the string to some sort of mechanism. We'll just say, attach it to some sort of mechanism. And the string gets taut, and here's the table, and then here's a pulley. And over the side of the table is a mass. And the weight is going to be mg. Mg is the tension. We know from if we can assume a massless frictionless pulley, I know there's a tension and a tension. Well, tension is going to be equal to mg if it's sitting still. So I can figure out the tension in this experiment, and I can figure out the mass density, and that's going to give me the speed of propagation of that wave. Now, the speed of propagation, if you studied chapter the videos, you realize that the frequencies, the characteristic resonant frequencies that, let's say, a guitar or a violin plays, depends on the mass density. It's like, what is it? V is NV divided by 2L. I think that's what the formula is. And so essentially your resonance frequencies are going to be N equals, N is going to be like 1, 2, 3, so on and so forth. So the notes that your guitar or your violin play are going to depend on the speed of sound. So if you go and you're about to have a violin recital, and what's the first thing your teacher does? Well, your teacher is going to, my daughter played the violin. She had a recital. There was the main teacher who was the violin teacher, but she had a friend who played the piano. So her friend would play middle C in the piano. Sometimes she'd play a piano accompaniment with the violin, but she'd play middle C in the piano, and then my daughter would have to play, or try to have to match that, or at least the teacher would try to match the little C. What's the teacher looking for? Well, if you looked at my video, the teacher's looking for beats. The teacher hears beats, then that means the frequencies are not aligned. You're not in tune. So what do? Well, she tightens the string, or maybe reduces the tightness. She changes the density. She changes the tension, hence changing the speed of wave propagation, and hence changing what the I apologize. This is frequency. F sub n is the resonant frequencies. Hence changing the frequency. So what does middle C supposed to sound like? Well, if you change the tightness of the string just right, which changes the propagation of the wave on a string, that'll change what the notes are, what the frequencies are that you hear. All right. So again, the tension in the string is very important. So when the violin teacher is changing the tightness, or if you do that in the guitar, you notice you can change the tightness on the guitar string. Well, that's what you're doing. You're changing tau, so that you change V, the speed of wave propagation, and hence you change the frequencies that you hear on a string instrument. All right, and so that's what's important here. So when you're changing the density, so I'm sorry, the tension. So let me go back to the lab. That's why this is important. All right, so going back here, we notice that I just automatically have it set as high tension. All right, but if I decide, so what am I expecting to happen? Well, from what I just explained, if I reduce the tension, I would reduce the propagation speed. And remember that the propagation speed depends on, it's proportional to the square root of the tension. All right, and so it's not going to be a direct proportional relationship, it's going to be a square root relationship. So if I take the tension, let's say down to maybe the middle setting, I'm going to notice that the wave is going to slow down a little bit. It's not going to go as fast. The propagation speed is not going to be as fast. And if I take the tension to really lower it, then I'm going to have a real slow wave. You know, so essentially I've reduced the tension and the propagation. I mean, again, this is an extreme case here, but you can see that the wave is taking a month of Sundays now to go from one side to the other, as opposed to if I put the tension all the way up, we'll see that the waves are going across just fine, right? So again, there's a relationship, and it's a square root relationship. Again, the velocity is proportional to the square root of the tension in the string. All right, so how would you answer this question? Well, define tension in everyday language. A tension is the tightening force in the string. I mean, it's the same tension that we studied when we talked about forces back in chapter 4. Explain how the wave behaves as the tension changes. Again, the speed of wave propagation is directly proportional to the square root of the tension, as I stated. The greater the tension, the greater the propagation speed, right? So that's how you roughly how you'd answer number 3 on page 3. Page 4, damping. Damping, if you watched my video on oscillations, damping is the friction in an oscillatory system. So for a mass in the spring, damping goes as the velocity. All right, and so with damping, we talked about friction. We've talked about sliding friction. Well, damping is the actual friction in an oscillatory system or a periodic system. And what's it do? Well, let's kind of imagine here for a moment. Let me increase the frequency a little bit so I can see more waves. Let me make it high. All right. So I want to kind of get the effect of, I want to see more waves. Maybe, all right, there you go. So we can kind of see right now that we have a wave train. I have damping down to 0. And so what I should see is the same kind of waves going on forever. I should see the amplitude right at the oscillator being about the same as the amplitude when you see it going out that window. All right. So again, the amplitude should not change. Now, what happens if I increase the damping? The damping is friction. So when I increase the damping, what's happening is friction is taking energy out of the system as the system moves along. And remember, energy goes as the square of the amplitude. So if energy is being reduced or is being released out of my system because of friction, I should see the amplitude reducing. And it should be reducing by the amplitude should be about the square root of the energy. Now I'll write this on a whiteboard in a moment. All right. So what I should see is the amplitude should be greatest near the oscillator. And as you move along the horizontal axis, you should see the amplitude reducing. So I put a little damping in, you'll see the effect, not so, slightly. Okay, you kind of see the effect now. Again, I have the damping set up to about medium. You notice that the amplitude is greatest near the oscillator, and it pretty much dies out. Or it's not very big by the time it gets to the window to the right. And if I really increase the damping, I'm just going to kill the wave, right? So I might have one pulse and it just dies, right? By the time it gets to the window, it's flat. All right. And so what's happening is energy is being dissipated out of the system. So essentially, if you want to see a nice, beautiful wave, turn off damping. So essentially, well, what's happening? So how would I answer this question? Well, for A, damping is a frictional force in the string, right? That's what it is, the frictional force. And let me stop sharing for a moment. Let's go back to the whiteboard. So what's happening? Again, please do watch my videos. But what's happening is, as I've stated and shown in my videos, the energy of a wave. The energy of a wave E is proportional to the amplitude, capital X squared. Proportional to the amplitude squared. So as energy leaves the wave, so damping causes energy to be dissipated. Which is evidenced by a reducing amplitude. As the wave propagates. And I know how that amplitude should reduce. I mean, if the energy dissipation is I don't know, so whatever the energy dissipation is, the amplitude will go as the square root of that. So if I imagine some sort of frictional energy, I'll call it E, I'll say E sub F is frictional energy, we'll say. I have some energy, some frictional energy, or non-conservative work, maybe is a better, more official term. I have some sort of non-conservative work that's that's being done by the frictional force. I should see that proportional to actually the amplitude reduction. Amplitude, well, you know what? This is probably fine the way it is. I mean, you see that the amplitude goes as a square, right? So you see there's a direct relationship. I mean, I'm just complicating things. Any question about that? Okay. What else? That's the bottom of page 3. Page 4. I guess the question would really be, well, what do you see? Well, you see. Let me ask you, because can anybody tell me? Can anybody tell me what the similarities and differences are? What you see on? And I guess this is number 5, which is on page 4. Can somebody tell me what you see that are similarities and differences of these two waves? Anybody? You see, anybody see those two waves in front of them?
I think for the top wave, the frequency is a little bit, or no, hold up. The tension might be a little bit higher, no, lower for the first wave. That's what I think.
Well, what I see actually is it looks to me like, I mean, in this span, I'm seeing about 1.5 waves, and looks like I'm seeing about, I mean, I'm seeing about 2 waves in the upper span. I'm seeing about 2 waves in each case, so I think the frequency is the same, and the amplitude, how high the wave gets above the above or below the horizontal axis. To me, I see the amplitude being the same too. What I see when I see this, the similarities I see are the amplitude and frequency are the same. The difference to me, what I see is the difference is definitely the phase. One wave is out of phase with the other.
Is it the time, the 0.20?
Yep, that would be right. You're absolutely right. one wave is one wave got a head start. You're absolutely right. Great observation. Yeah, so one wave got a head start, so it's just further along. It's the same wave, it's just further along by 0.20 seconds than the other wave. Everybody see that? So again, they're the same wave. It's just they're just out of phase. So I just wrote down in the bottom. I wrote similarities. On the left column, I wrote. Well, I'll write down what. I'll show you what I wrote. I mean, I'll kind of just. I didn't write much. I just said, I mean, if I was you doing this lab, I would have said, well, looking at that page 4, I would have said something as simple as this. Similarities. Differences. This is all I was right. Similarities I saw, amplitude and frequency. Basically you're just looking at a picture basically. And the differences I saw was phase. And as Homero said, I didn't even see that. Yeah, it's off by, literally it's off by 0.20 seconds. So it's literally off by one wave just got a 0.20 second head start. So they're just different by a phase. They're the same wave, just one is advanced in time by 0.20 seconds more than the other. That's all I'd say there. All right, last page, number 6. So I'll show you what I did. This is where I had a little confusion about what Dr. Edmonds wanted, and you can be just as confused as me. That's fine. I'll just kind of explain what confused me, and I'm not really sure. I haven't had time to talk to Dr. Edmonds, and I think what I did is probably perfectly fine. So let me go share. Let's see. Yeah, let me share my screen again. Okay, so we're back to the lab. Now it says make a wave with the oscillator with no damping. Okay, so I turn off damping. I got everything back. Let me get the frequency back to what it was before. I just put it where I did to show more waves. I'm going to set it back to about 1.5 hertz. All right, damping I turned off. Tension I maximized. Now measure the vertical and horizontal location of a green ball with the ruler and record the time. Okay, and then use the little it's a little fast forward button, I guess, if you will, to collect data to make a table of a time, vertical and horizontal positions of the green ball. Make sure to include the observations when the green ball is above or below the middle line. Okay, what I don't understand is every green ball that I see is just going up and down, up and down, up and down, right? So there's no green ball that's actually transferring in the X direction. So what I did is I just said, well, I don't know what he means by the horizontal. I just wrote all zeros in that column. I looked at the vertical and I just picked different times. So what I did is I slowed the frequency down so I can most easily follow it. I took the frequency down to all the way down to like 0.1. I just made it very, very boring. And I took it down to 0.1 so I can actually analyze the y-axis. And then what I did there is I then took, I clicked the ruler, and I clicked the ruler, and there's the ruler. So what I basically just did is I reset. Let's see, the reset button here. I'm going to restart. Well, let me restart. And let me hit the reset. Let's see, I think this green thing is a reset. Nope. Ooh, that wasn't what I wanted to do. Never mind. All right, well, let's just start it again. So oscillate. Okay. All right, oscillate. No, I don't want to do that. Give me a second here. Slow motion, let me pause it. Okay, amplitude frequency is fine. I want to take damping back down to 0. I want the ruler, and I guess, do I really need, I need the timer as well. Yes. So I'm gonna essentially time, this is what I did. I made on the table, the left column is a set of times that I'm going to do. The vertical is the vertical reading that I'm going to get from the ruler. I'll kind of show you how I'm doing that. For the horizontal column, I don't really understand what he means by that. So I set the horizontal columns, I just set it to zeros. Because I want to watch the ball that's lined up with 0 on the horizontal ruler. Okay. I don't know what he means by follow a ball in the X direction. Follow some ball. I don't. I'm going to follow a ball that's just going to go up and down. Okay, and so all I'm really going to do is the right column. The way I did it, I just set the right column all the zeros, and I'm just going to get time vertical measurement pairs. All right. So notice right now that let me kind of get this thing set. Let me stop this thing. Stop. Oh, no. All right, stop. All right. Yeah. I'm hitting a little that little arrow that he talked about to kind of set it to where I want to have it be. Okay, let me start it. Well, yeah, let me start it right at the horizontal line. So I'm just resetting it so that I get close to the horizontal line as possible. So right now I'm in pause, and I'm just setting the far left green ball so that it is lined up with that horizontal dash line. Now, I have the system. I have it in slow motion. The amplitude is at 0.75 centimeters. The frequency is at 1.5 hertz. I have the tension set to high. And now what I'm going to do is I'm going to select the go arrow, the play arrow on the time. Right. So I'm just going to do that. Let's see here. Now I want no end. I think, yeah, there you go. I selected no ends. I don't think it really matters for the boundary condition on the far right. Now what I'm going to do is I want to hit the little advance button, and you should see the time advancing too. All right, and so I'm going to kind of take it. I'm going to advance it to. Okay, so right now I started off at 2.6. If you look at the ruler, the ruler's in centimeters. You see the 2. So you have 5 increments. So the next increment may be 2.2, 2.4, 2.6, 2.8, 3, 3.4, 3.6, so on and so forth. Every increment is basically a 0.2. So my very first time measurement was 0 and 2.6. So I said time t equals 0. I started at a vertical of 2.6. I'm going to take it to 3. And so I'm going to let the thing, oh, you know what? Let me restart this again. I want to do it the way I did it. I started it so that it was starting to go up instead of going down. So give me a second here. Bear with me. I just want to match the data I did this morning or get close to it. All right, so there we are. I'm going to reset the timer. So the timer's back to 0. Hit the go button on timer. So I'm starting the experiment again. Before, when I advanced it, the wave wanted to go down first and go back up. The way I did it, I went up first. So I just kind of want to match that data. So, all right, so I'm at 2.6. So my first data point still is time 0, vertical height 2.6 centimeters. I'm going to take it to, I did a vertical height of 3. So I'm going to kind of advance, hit the little advance button until I get to 3. And when I do that, I get that to be you know what? Hang on. I forgot to do something. Bear with me, sorry. You're not going to get the same data I'm getting. I remember I took the frequency down to 0.1. So I screwed this thing up. So let me start this again. Bear with me. I gotta get it back to 2.6. All right, so this thing's gonna be really flat. I want to be able to see. I want to actually be able to see something that I can actually graph. All right, I want to reset my timer, get it to go again. Hit go. I want to take the frequency down to actually around 0.1. I want the frequency to be very small, so it's easy to see things. Okay, you're not looking for a pretty picture here. I'm just looking for measurements. All right, so my frequency is 0.10. That's important here. The amplitude I don't care about. Frequency is 0.10. The damping is all the way down to 0. The tension is high. Okay, now I'm going to start going. So I'm going to hit the advance button. I'm at 2. Again, my first data point again is time 0, vertical 2.6 centimeters. I'm going to advance it to about 3. The way I did it. So let me advance this guy to about 3. I'm watching the green, watching the green ball on the far left. So it's at 2.8 right now. I'm just hitting the advance button, slowly advancing it to 3. All right, it's not an exciting experiment by any means. All right, so I advance it. The green ball on the far left is almost there. I'm just hitting the advance button. And here we go. We are at 3. And the time, I read the time, it's basically 0.83 seconds. All right, so 0.83 is what you see there. Give me a moment. Redo these with you guys. All right, 0.83. You know, well, I had 0.72 when I did it, but we'll just do 0.83. All right, so my data at this point should say time 0.83, and I would say vertical is 3.0, right? All right, the next data point, I'm going to stop at about 3.4. So I'm going to hit the advance. So I'm passing 3.0. I mean, I probably could have picked something bigger than 0.1 hertz, but you know, it's fine. So I'm about to pass 3.2. I'll go up to about 3.4. You know what? Let me increase the frequency on this. I apologize. Let me increase the frequency. This is a little bit too low. I take it to about 0.5 hertz. I did it a different way this morning. This is a better way. Let me just increase. Let me redo this data. Sorry about that. I'm improving as I go along. I'm evolving. I'm going to keep the same vertical lines that I did. All right, let's do this one more time. Otherwise, this is going to take forever. All right, so let's get this back to 0. Let's just kind of get myself back to where my starting point. Actually, let's just make the frequency 1.0. Sorry, guys. 0.7. Yeah, I'll do 1.0. 1 hertz. All right, let's get it back to where I had it. No. All right. Stop. All right. Sorry. Okay, there we are. All right, so one more time for good. All right. So again, I'm at my first data point, again, is time 0 and vertical line 2.6. All right. Now it's going to go a little faster now. So now I'm going to hit the advanced button and I'm going to take it to 3.0. There'll be fewer clicks this time. There's 2.8. There's 3.0. You look at the time there, it's 0.07. So the second data point I get is 0.07 and 3.0. Continuing, I'm going to go to 3.4. So I'm going up to 3.2, clicking the advanced to 3.4. Almost there. Again, I'm eyeballing it. And I do that. I see the timer is now 0.23. So far my first 3 data points, my time is 0 and my vertical is 2.6. My time is 0. The next row, my time is 0.07. My vertical is 3.0. My time is 0.23. My vertical is 3.4 in my first 3 data points. I'm going to go back to 3.0. I'm going to let it go to the top. It's going to max out the top, and then it's going to come back down to 3.0. So it's coming back down to 3.2, getting down to about 3.0. And that's probably good enough. And you read the timer there, it says 0.41. So my fourth data point is 0.41 and vertical 3.0. I next want to take it down to 2.6. So keep hitting the advance. 2.6 is back to the horizontal line, the horizontal dash line. All right, so 2.6 is about there. That's 0.50. So I mean, I've gone from the dash line up. So I've gone basically. This is essentially like half a cycle. Let's see here, 0.50. So the next data point was 0.50 and 2.6. Okay, moving on. I'm going to go down to 2.2. There's 2.4. My green ball is now, again, I'm following the green ball on the far left. And that's around 2.2. And it looks like I'm at about 0.59 seconds. So my data point, the next data point becomes 0.59 and 2.2. I'm going to take it down to about 1.9 now. That's what I did this morning. So take it down to about 1.9, roughly about the bottom of this. Okay, 1.9 is about 0.69 seconds. And my vertical is 1.9. And then my next one, I'm going to take it back to 2.2. So we're going to bottom out. It's going to come back up to 2.0 and go to 2.2. Roughly about that, 0.90. So the next one I see is 0.90 and 2.2. I'll take it back up to about 2.8. So I'll blow right through 2.4, 2.6, back to about 2.8. Roughly. And I see 1.03 seconds on my timer. So my next data point is 1.03 and 2.8. 2 more data points. I'm taking to 3.2. I'm going past 3.0, going to 3.2. My green ball, the vertical measure will be 3.2. I'm at 1.12 seconds. Finally, I'm going to go and take the last data point of vertical 3.4. Just for good measure. Looks like 1.22. So if you look at my data, and I hope you do it yourself here, but the far left column that I got, the times I got, I'm just going to read down my time column. I got 0, 0.07, 0.23, 0.41, 0.50, 0.59, 0.69, 0.90, 1.03, 1.12, 1.22. And my vertical height column, if you will, if you read that down from top to bottom, it's 2.6, 3.0, 3.4, 3.0, 2.6, 2.2, 1.9, 2.2, 2.8, 3.2, 3.4. And what I like to do is I can make a graph of that. All right, and so I'll go into Excel and make a graph. So I'm going to stop sharing this screen. I don't know how to do the horizontal. Again, as I said, I'm leaving that horizontal column just as zeros. I don't know what it is, but I'm going to go and graph the vertical. So I have. See, I'm going to bring down this. I'm going to bring up my Excel spreadsheet I did this morning. Put new data points in it. So give me a second. Wave data. Bring up Excel. So we're almost done. I'm just bringing up Excel right now. So a lot of this I'm going to do is very similar to what I showed you last time with Excel. So I kind of done the work already. I'm just going to kind of show you the results. Just making the scatter plot and taking the scatter plot and making it its own tab. Hang on one second. I'm trying to bring Excel up real quick though. Everything slows down with this Zoom software. All right, it is up. Okay, I'm gonna go to my data now. I'll share. All right, I'm gonna share with you now. All right, so quite simple. The right column, the right column is given my Y column. The left column is my time column. Now my times are wrong. They're the times I had from this morning, but my Y column is my vertical column. So it should match what we just saw. 2.6, 3, 3.4, 3, 2.6, 2.2, 1.9, 2.2, 2.8, 3.2, yeah, 3.4. The right column. So I had a much reduced time, or a much increased time, because I had a much reduced frequency. So let's put my new values in. So I had 0, 0.07. Oh, hang on, that was right. Number one. Try that again. 0.07. 0.23. 0.41. 0.5. 0.59. 0.69. 0.9. 1.03. 1.12, and finally 1.22. Is that right? 0.0, 0.07, 0.33, 0.41, 0.5, 0.59, 0.69, 0.9, 1.03, 1.12, 1.22, yeah. And so I already did the scatter plot. And let's see what the chart looks like. And if you can see this, you'll notice that the chart looks like a sine wave. You guys see that? You know, I'll make it darker. The data. So I'm highlighted it here. So that's the data. The bottom axis, the time axis, the vertical axis is the y-axis, and I can make this black instead of blue. Maybe let's see. As you can see, I sometimes look like a goofball when it comes to Excel. So let's see. Yeah, okay. The marker, I want it to be black. Here we go. It shows up better. There it is. All right. So now marker is now black. All right. So this is the data that I plotted. I plotted, 2 columns of data. I did a scatter plot like before. As you can see, the y-axis is in time. That's really the oscillation. Is essentially, it looks like a sine wave in time. All right. And so I'm not, again, that's me following the very far left green ball and its vertical displacement. Any question about that? I wouldn't do anything for the horizontal position because I don't really understand what he wants, because he says follow a certain green ball. I'm not really sure. I follow a certain green ball, and that particular green ball does not move. So how do the graphs help you understand the characteristics of waves? Again, the graph that you see is really the position of the oscillator. But you notice that the oscillator creates a wave. So there's a relationship that the oscillator will create the disturbance that you see in the form of a wave. It creates a disturbance that propagates as the wave, right? And so, and then for part D, predict how the graphs will look if you increase the damping and test your ideas. Well, all the damping is going to do is just cause your graphs to your horizontal graph, whatever it be, you would see that there would be a reduction in amplitude in the x direction. I'm not really sure how you would graph the x direction with respect to what you have here in this data. But at any rate, the damping would just cause the wave to look like it's reduced in its amplitude over time. All right, I'm going to stop sharing. There's only one more thing left, and that is number 7. And 7, all you really want to do is kind of give a description of what you see. And so if I go back to sharing, I'll go back to the wave. And one of the important things about waves, as you can imagine, is what are called boundary conditions. Boundary conditions are what the ends of the wave look like. The wave is going to propagate, but the wave has to be someplace in certain places. It has to have nodes someplace. So a boundary condition, like let's say like on the ends of a string, the string is tied to 2 locations. You have to have nodes there. Those are boundary conditions that affect what the rest of the wave looks like. Or if you have a air tube, let's say a tube that's closed to one end, like a clarinet or a trumpet. I talked about this in my lectures. Then you're going to have a node at the end of the closed end of the tube, because that's where the air stops. If the tube is open at both ends, you will have no nodes at the ends. Your nodes would appear other places. So the boundary conditions, basically, what are the conditions at the end of the confines in which your wave is propagating within? I mean, that's going to determine what the wave looks like. All right. And so in this particular case, one end of the wave is attached to the oscillator. It's being driven by the oscillator. The other end is, I mean, essentially what happens to the end, what happens to the wave at the far end? Well, what we've been looking at all along is no end. We're allowing the wave to go to infinity. What happens if I clamp the end? What if I fix it? I fix it at the end. Now I'm going to have what's called a standing wave. So instead of having something that's a free end, what's going to happen now, what I'm going to now have is I'm going to have a wave that looks like it's oscillating in place. Let me kind of speed up the frequency a little bit here. It's going to look like a wave. It's going to look like a wave that would be on a guitar string or a violin string. It's going to look like it's oscillating in place. There will be a node at the far right end. So the wave, no matter what the wave does, the wave cannot move at that node. If I increase the frequency, I'll have more of a well-defined wave. But again, I'll start seeing, nodes forming, but there's not going to be any. There will always be a node at the far end. So you'll notice that eventually it looks like it's essentially moving in place. And when it finally, there's a lot of things that need to die out first, but eventually the wave looks like it's moving in place. And all I did, so there you go. It looks like it's basically oscillating in place. That's because I changed the boundary condition at the end. I fixed it so that it is not a wave going forever any longer. Now it's a wave that absolutely has to have a node, has a boundary condition. It must be zero, must have zero amplitude, or it must have no movement. It must be a node at the very far end where I have it clamped. So I made a boundary condition. Because that boundary condition, I have changed the oscillator. I haven't changed the oscillator at all. Boundary condition changes the entire wave, the entire nature of the wave. Now it is a standing wave. And if I look at a loose end essentially means now I'm going to allow the wave to move up and down, but it's going to be going like up and down on a pole. So now what's going to happen is, let me kind of reduce the frequency a little bit here. I think I've caused this thing to go crazy. Take it back down to about 1.5. So it's going to go up and down on a pole now. So if I have it, let me kind of get this thing to stop being so crazy. Actually, let me put it at no end right now, so I kind of get it to kind of settle down. Yeah, let me get it to settle down here. Take it down to about 1.5 hertz. Let it settle down. All right, so now it's behaved. Now let me allow it to be at a fixed end again. There's a wave with no end. Now I'm going to set a fixed end. So I'm going to change the boundary condition such that there must be a node at the far right. We're going to have, we're going to have a standing wave that's not going to be quite as crazy. So we'll see a similar standing wave pattern by time all the transients die out. And then when the loose end, it's going to be like I put a pole, and it's a ring on a pole, and that's going to cause a change. All I've done is I've just changed the boundary condition, and I've changed the nature of the wave. So kind of describe what you see there. So we investigated fixed, loose, now manual and pulse. All right. So what I've done is I have an oscillator. So let me go back to no end again, get it to kind of settle down. Now what I have is a periodic oscillator. What if instead I decide to do a pulse? So no longer an oscillator. Now I'm just going to basically set a pulse. Right. So right now nothing's happening. I'm gonna fire off one pulse. Boom. And I'll allow that pulse will then propagate all the way down. And so that pulse is going to propagate down. Now if I decide to do two pulses now. And that's kind of the way we actually transmit information. And we transmit information in waves. We control how we, it's basically depending upon how I modulate this, or I can actually control the wave pattern, the wave that I send, the information that I send along the wave in the communication system. So that's just setting a pulse, just one pulse, not something going on in periodic motion forever, just one pulse. Or number of pulses will determine, you know, maybe I'm sending a message. Now manual would then be that I can kind of control the up and down nature of this. So instead of it going by some oscillatory system, I can kind of control it myself. I can move the thing myself and make the wave go as I wish. So no longer is it a nice being controlled by an oscillator, it's being controlled by clumsy me, right? And so essentially I'm creating a wave. So it's no longer just a pulse. Now it's me, whatever I want, whatever disturbance I want to make, that disturbance propagates. That's what the manual option does. And kind of just, you know, all you really want to do on number 7 is kind of just try these out yourself and record in your own words what you saw. What do you see when you change the end or boundary conditions, as we say, the fixed, the loose, or the no end? And what happens if you change, if you drive the wave, you force the wave with an oscillator as opposed to manual, as opposed to a pulse? That is it. And then what I would just do is I would turn in a plot that looks like that Y versus X plot that I showed you. You know, that little sinusoidal plot where we went through that data table we filled out. I would turn in that Excel a plot of that Excel plot that represents that data table, the Y versus the X. Other than that, I mean, I think this lab is pretty straightforward. That's all I have to say. Does anybody have any questions? How many of you guys are even still here? I see 9 of you. All right, great.
We're here, but no questions.
Okay.
Thank you.
You betcha.
I have one question. From what I heard is that we're at the end of the semester, we could redo one of the labs that's our lowest grade.
Yeah, I'm gonna send out. We're like, so this thing's going so fast. I actually am going to send out an email with an extra credit assignment, a real simple assignment. It's a little writing assignment, maybe like 1 or 2 pages that'll replace your lab grade. I mean, I can kind of tell you what it's going to be. It's going to be. I always like to. One of the things I like to try to do, and I give talks on this all the time, is I try to encourage the involvement of women in science. And so one of the things that people don't seem to realize in history is that most people who've ever lived did not get a chance like you guys are getting. Didn't have a chance to form their own life. The only people that actually had any kind of chances whatsoever were basically Christian white males. And so, and that's not only unfair, but it's just plain stupid, quite frankly, because look at all the great talent. You know, the female Isaac Newton didn't get a chance, or the black Isaac Newton didn't get a chance. I mean, all the various people that didn't get a chance to be successful, you know, and so we as a human race really hurt ourselves, right? And so what I try to do is I try to, and I'll send us an email about this, but the assignment is to write a 1 or 2 page little report on your favorite female scientist. And there's a lot of great female scientists out there that have done significant things. So I mean, I can list, for instance, Lisa Randall, or Judith Resnick, or Sally Ride among the physicists, or Vera Rubin. We know about dark matter because of her. Or you look at you know, all these various, you know, female scientists. I'll essentially give you a list. You know, Rosalind Franklin, for instance. You know, you hear about the DNA molecule. Well, Francis and Crick would be clicking rocks together. It wasn't for the work that she did. She did all the heavy lifting. Did she get the Nobel Prize? Of course not. But she's the one that did all the heavy lifting to actually give these guys anything. So we have DNA today because of her. That's a woman. You know, so some of the, you know, one of the first computer languages ever made was a language called Ada. I mean, named after Ada Lovelace. Very first computer language, you know, basically created by a woman. So all these various things that great contributions that women have made. So I'll send an email about that, and and essentially you just write a really nice report, 1 or 2 pages. Just don't kill yourself over it. And I think you do a good job on that report, then I'll just give you a replacement lab grade. So that's kind of like what I want to do. That's just one way of helping, and another way of getting the message out there that, of honoring women and particularly female scientists. That's something that's important.
Okay, so there's no right from wrong, right?
What's that?
Just do a report, but there's no right from wrong.
No, I mean, try to be as accurate as you can, but no, I'm not going to grade it.
Okay.
I'm not going to say, I know about Lisa Randall. You messed up there, buddy. No, I'm not going to do that. Of course not. But try to make it accurate. I mean, it's a learning experience for you.
Okay, sounds good.
Yep.
Professor,
So that's the extra credit. Yes, I'm sorry.
would there be a key for the review?
I'm going to, well, I don't give answer keys because it's an exam. I mean, I did go through a set of problems that do have the right answers. I did about half the problems on the board, about half, I would say similar problems. And then the other ones are problems that I either worked out directly. I mean, the ones I just told you to look at, they're either OpenStax problems that I actually did in the videos, or they are problems that and I will post answers to the ones. I've been a little bit tardy in that. I owe you guys answers to problems all the way through chapter 8. I'll put those on the board. I'll put those on Blackboard here within probably the next couple hours. I have to redo a couple of the scans. I had a couple of things that were screwed up, so I'm gonna redo a couple of scans, and I'll post those on Blackboard either tonight or tomorrow. So yeah, so basically you've gotten about half the problems. I gave you very similar. I worked out a problem that's very similar, and then the other half the problems I gave you similar problems to look at, and those problems have all been either done by you in the homework, and I'll give you solutions, or they've been done by me in the videos. All right, so you should have answers to everything in that sense. Okay.
And one more question: will you be sending out, like how you did for the last test, the homework answers?
Yeah, I just said that.
Oh.
I'm a little bit behind on that, but yeah, like I said, I owe you up through chapter 9, so those will get out briefly.
Sorry, I didn't hear that.
Yeah, it's okay. Yeah, I'm going to do that either tonight. The problem is the school system always shuts down at 2 in the morning, so I end up getting busy and stuff and other things. And yeah, I shouldn't be up at 2 in the morning, but I always am. But again, that kind of sets the end of my day as far as the school goes. It's that system shuts down every single day for maintenance at 2 o'clock in the morning. So that means if I'm going to post anything on Blackboard, I better do it before 2 o'clock in the morning. So, I mean, that's in about, I guess, what, 5 hours. Any other questions?
Professor, on the homework, what should we expect to turn in by next Tuesday?
I can barely hear you, Preston.
Sorry, is my mic working?
It's working a little bit better now. Yeah, I think your mic had some trouble last time too.
Yeah, unfortunately it is. If you can hear me, what homework is due next Tuesday?
This Tuesday, the homework that's due is going to be a bunch of homework. It's going to be kind of a remnants from last week, which was chapters 8 and 9. And then the homework that was actually due this week would be 10, 16, and 17. So hypothetically, you would turn in homework for chapters 8, 9, 10, 16, 17.
Sorry, for next week.
Next week, well, the homework for the chapters that we're officially covering this week, and I put videos out, is chapters 11 and 12. And so the homework that would be due next week would be chapters 11 and 12.
Okay, guys.
There's a fluid mechanics video, and then that fluid mechanics is the end of mechanics at this point. At that point, mechanics is done, and we've already done waves, and so now what's left is thermal physics. So chapter 12 is the first of 4 chapters in thermal physics. Thermal physics is chapters 12, 13, 14, 15. And as I said, exam 3 will be over chapters 10, 11, 16, 17. So it'll be what's remaining in waves, and then I'm sorry, what was remaining in mechanics and waves. And then the last test of this semester will just be a thermal test. Any questions?
I'm good, sir.
Okay, thank you.
All right, thank you.
For the homework that's due today, do we send it all in one email?
You can. It's just I've had people do all kinds of different things. I guess I mean, what makes it complicated is I have the homework from last week, right? So if you want to send chapter 8, 9, 10, 16, 17 all separately, you can. If you want to put it all in one single document, you can do that too, as long as it's in order. As long as I'm not fishing around trying to figure out, okay, you got the chapter 9 problems all jumbled and stuff. I had to do that. I mean, first of all, I'm not very happy when I have to do that. And then the other thing is, I may miss a problem, so you're not doing yourself any favors if I do that as well. So it's a lot easier when you put everything in order. That way, I'm going to have much less likelihood to miss anything.
Okay, thanks.
Mine's all on Dropbox,
Yep.
by the way.
Yep, I got you figured out finally. Anybody else? All right. Well, I guess we call it a done deal. I'll see you guys on Thursday. Have a good night.